So this week, I'm very pleased to introduce Richard Arnold. So Richard and I were grad students together. I know it's very boring for people to hear about these stories from the old days and so on, but I haven't seen Richard for quite some time. But I came across his research recently, and then it was pointed out to me that the time zone in New Zealand actually makes it completely reasonable to have somebody give us a Zoom call. So suddenly it became sort of much more realistic to actually ask him to do that. So Richard originally trained in, well, physics and astronomy in particular, but then went into statistics, and he's applied his statistics knowledge to a very wide range of phenomena, with a sort of common thread often being things to do with rotation. And he's going to talk to us today about rotational statistics. So it's all yours, Richard.
Thank you. Thanks very much for the invitation, Douglas. It was really nice to get your email. And this is a talk summarizing a whole lot of work that I've done over recent years with a couple of collaborators on directional statistics. And I got into this because a geophysicist walked through my office door with the question, how much information is there in an earthquake? I didn't anticipate when he asked that it was going to be such a geometrical question, and I'll explain why it is geometrical in a second. So let me press the share button and share my screen. So I'm hoping that's all visible now. So the principal collaborator I've been working with is Peter Jupp, who wrote the book Directional Statistics, which is one of the standard texts in what is quite a small field. It's smaller than it deserves to be. And Helmut Scherbin is a material scientist, physicist, mathematician, working in structure of solids in Freiberg. They have both retired. So I think this collaboration will go on until we all get too sick to carry on. I'm hoping it's not me first, since they're a little bit older than me. But anyway, we'll see. Okay, so the game is to do statistics with highly symmetric objects in the presence of high degrees of symmetry. And crystals are an obvious example of highly symmetric objects. A cubic cell can be transformed 48 ways and still be the same object as it was. But it does turn out that earthquakes have got symmetries which are of interest as well. And that's what led me into the question. So the real question that I started on was estimation of tectonic stress, so the stress that drives earthquakes, using information from earthquakes themselves. And New Zealand is quite tectonically active. We're on the other side of the Ring of Fire, and there's quite a lot of action here. I don't know what it's like in Vancouver. I guess you must feel earthquakes from time to time, and we certainly feel them with some regularity. So Directional Statistics 101 starts with a picture like this always. So this is some data of wind directions in the Italian Alps, and we've clearly got quite a spread of wind directions, but there's a predominant northerly wind at this location. And if you do what people always do in statistics, you add all the things up that you've observed and divide by the number of things to get an average. You get the simplest average. It doesn't make sense, and there's a very obvious reason for that, and that's the location of zero. If you move zero away from where all the data are, this average can make sense. But if you have, it just doesn't work in general to move zero away and put it where there's a gap, because often there isn't a gap. So the problem is that 355 degrees and 5 degrees ought to average to zero, but they average to 180, and that's inconvenient. So we end up with this silly average. So the solution of this is to treat all these data as unit vectors. So we have cosines and sines, and then we view these data not sitting on the circle, but as sitting on the full plane, and then we take the average of the unit vectors. And the direction of the unit vector gives us the direction we want. So the mean of the unit vectors is not itself a unit vector, but it points in the right direction. And so the scaled version, the unit length version of that average unit vector has an angle pointing in the sensible mean direction. But its length also has information that if the more widely spread the data, the shorter the mean vector is, and that is an immediate measure of dispersion. So the averaging operation gives us not only the mean, but effectively it gives us the variance as well at the same time. And if the data are roughly uniform, that unit vector will have had length 0. So the thing that is happening here is we're taking the scalar angle and its symmetry, and we're embedding it in a slightly higher dimension space. So instead of just a one-dimensional scalar, we've got a two-dimensional object, even though it only has 1 degree of freedom, but it respects the symmetries. So the cosine and sines, of course, respecting the symmetries we want them to have. This leads to the classic distribution on the circle, which is the von Mises distribution, where the closeness between angles is measured by the scalar product between 2 unit vectors on the circle. And then we have a scalar parameter kappa, which tells us how concentrated the data are, or the distribution is, around its mean mu. And our data are these unit vectors. So in scalar form, it's then a distribution on theta. But the kernel of it is cosine. It's the cosine of theta minus theta naught. And this leads to a whole lot of statistical tests and statistical constructions. And this distribution is the analogy of the normal distribution in a regular unbounded scalar case. It's often the case, and this is especially true in geophysics, that you don't really care about the direction so much as an axis. You don't really care whether you're talking about north or south, because it's the north-south axis you're interested in, or some such similar axis. So every data point can be expressed in 2 ways, and this ambiguity can then lead to a confusion about, well, how do I calculate means and variances in this situation when the symmetry isn't plus multiples of 2 pi, it's plus and minus multiples of pi. So what we do here is we take the unit vector again, but we note that we don't care about its sign. So plus u is the same as minus u as far as we're concerned. And what we do is we embed this now in the space of 0 trace rank 2 tensors. So it's still only 1 degree of freedom, but we multiply, the basic idea is to take u and multiply by u transpose. So now its sign doesn't matter. I can flip the sign of u and this object doesn't change. I subtract off half the identity so that on average this object is a matrix of zeros if u is distributed uniformly, if these axes are uniform. And when you do the simple algebra to construct this object, you get these doubled angles. And this is something that's been known for some time, that that if you want to work with axial data, what you do is you take all your observations, and it doesn't matter which direction of any axis you've got, you double all the angles, then you treat them as directions, and at the end you halve the result. And that's the equivalent operation here is embedded in this doubling of the angles, cos 2 theta and sin 2 theta. So it's got the right axial symmetry. We subtract off half the identity, as I said, to make sure it averages to 0. And this is a trick that has been known for some time. I don't know who first came up with the trick of doubling the angles. But this is the implied embedding, or one of the implied embeddings. So again, the idea is you've got an object which has got a symmetry, and you embed it in a higher dimensional space, and there averaging works nicely and simply. So the scalar product here, you take the two if you've got 2 of these matrix objects, you multiply one by the other transposed, take the trace, and that gives you a scalar, and that's the scalar product that is going to be the core of measuring how close 2 axes are. And this one happens to have a normalization of a half. You can construct these T objects to have a different normalization, but it just doesn't matter. But the scalar product quantifies the closeness we're after, just like it did in the case of the simple angle. once you've done this, you're in this space where everything is smooth. There are no jumps the way we have from 0 to 360 being equivalent. So we can average just as we did before. So we take all the objects we're interested in, we add them all up and divide by the number of them, and we end up being able to construct a scaled version of this rank 2 tensor. So the rank 2 tensor gives us the direction of the axis we're interested in, and the scaling of it gives us the dispersion. But this is all then super convenient. And basically all of the statistical tests that you can construct for single directions rather than axes, they just carry over. Okay, so having those ideas in our pocket, we can then apply them in other settings. So this talk is going to be a summary of a number of different projects that I've worked on over the years and different applications of directional statistics to them. So this is the first one that I worked on, which is orthogonal axial frames. And I'll explain what a frame is in a moment, or now. So a frame for us, say in 3 dimensions, is 3 unit vectors at right angles to each other, x, y, and z. An axial frame is when you don't care whether it's plus x or minus x. So those things are genuinely indistinguishable and you're not caring about them. So an orthogonal axial frame is 3 orthogonal axes. They're distinguishable axes, so you know that x is different from y, but you don't know about whether plus x is different from minus x. They're equivalent. So you can have a single axis in 3D, say, or 2 axes which are perpendicular to each other, or you can have the triplet. So 2 axes and 3 axes are, of course, in 3D are equivalent to each other, because once you've got 2 axes, you've defined the third. 1 axis alone in 3D, of course, could have multiple axes associated with it. But if we're talking about a frame, we can have 2 axes or 3 axes are the same thing. Okay, so as we all know from our first forays into geometry in 3 dimensions, that you have a unit vector in 3D is defined by 2 angles, and a third angle defines an orthogonal matrix, which gives you the orientation of a frame, not an axial frame, a frame. You can point 3 orthogonal directions. What we have now is an orthogonal matrix where we don't care about the signs of the columns. The signs of the columns are arbitrary and we can flip them around at will. In this talk, I'm going to plot stereograms. I'll just tell you what that is. This is like looking down onto the top of the sphere, or geophysicists sometimes imagine we're looking at the underside of a sphere. We're looking down into a sphere cupping at us, with the center being far away. Nevertheless, it doesn't matter which way. Let's imagine we're looking down on the top of a globe. So we have x-axis to the right, y at the top, and z is the center. So a unit vector, is a point on this cap. Although it might be on the other side, it might be invisible. An axis is a pair of points at opposite through the center. An orthogonal frame is 3 identified distinct directions, and an orthogonal axial frame says I don't care, plus or minus 1, the 1 axis. I don't mind which direction I specify. That's an orthogonal axial frame, and those are the things we're interested in. So what we're going to do is we're going to carry on this idea of embedding. We've seen it in the plane. This is in 3D. And if you want to take 3 orthogonal axes and embed them such that you don't get the sign bothering you, we embed this as a triplet of matrices. They're going to be rank 3 traceless matrices. So you take each of the U1, U2, and U3 in your original rotation matrix, and then construct this object. It has a scalar product which looks like this, which is its scalar product is basically the individual scalar products of all of the columns with their respective ones when we're comparing two orthogonal frames. We square them to kill the sign problem and subtract off 1 to get 0 when we've got uniformity. And this happens to have the a normalization of 2, which we could take away and make 1, but it's arbitrary, so we haven't bothered. So this is, again, this is the same idea. This object, it looks exactly the same as the doubling angle one, but is now in higher dimensions. And this can go on into arbitrary dimensions as well. And our paper does that. But I'm going to talk about 3D because it applies to earthquakes. Key thing is here, averages are just as simple as ever they were. You add up these things, even though they are triplets of matrices, you add them all up, divide by the number of things, and you've got your object. So that's what that averaging looks like. It's averaging of 3 sets of matrices. And then the sample mean is unfortunately has to be found numerically, but you find the object, the rotation matrix in this form of a triplet of matrices that is closest to T bar. And once you've done that, that's your sample mean. And we have a measure of sample dispersion that comes directly from that as well. So once you've got these objects, you do the same thing to them, even though they have different structures. They're either a single matrix or a single number or a vector or a triplet of matrices in this case, but we do the same thing to them. We add them all up, and then we can find the mean that way using the scalar product that's implied. So just as an example, if you're doing a 2-sample test, you wanted to know, is this set of frame objects, does it have the same orientation as this collection of frame objects? We average one, average the other, and then you just do simple subtraction of the averages, and that gives you a test statistic. And then you compare that to the same test statistic where you randomly reallocate, relabel the objects of from your 2 original distinct samples. You randomly shuffle them between, recalculate this statistic, and see whether you have an extreme example, extreme value of D with respect to that random relabeling. So that works very well. And a lot of tests have got that character. There are a few tests which have proper analytic properties that we can work out. There's a test for uniformity, which is asymptotically chi-squared, which we can also use, but for many purposes, these randomization tests are just as convenient. And then this object, this embedding immediately leads to the generalization of that von Mises distribution, that distribution I showed you on the circle. This is what that equivalent is. The core of it is a scalar product between the object we're generating at random, that's the U object in its T form, in its embedded form, and the parameters are 3 traceless matrices. Symmetric traceless matrices are the parameters. And that gives us the frame Bingham distributions. And these are just generalizations of simpler cases that people have found before. And that leads to tests, as I've said. Okay, so what has this got to do with earthquakes? So what is an earthquake? An earthquake is when a small patch of ground, and it might be just as small as the size of the floor of an office, just a few square meters, that planar interface is weak and it breaks. So the molecular bonds that are holding it stuck shut, they rupture, and the plate, the blocks move against each other. So what you can see is that there's a plane and there's a motion within that plane, and that is what the definition of an earthquake is. In addition, of course, there's the scale of the motion and the amount of energy it's releasing. But geometrically, there's a plane and a motion inside it. So we have 3 parameters that summarize an earthquake's geometry, and they are the strike and dip, which are the angles defining the plane, and then what geophysicists call the rake, which is the motion within the plane. And we have 3 unit vectors that are going to summarize those. And the important thing about there's an ambiguity there is because, of course, we've got the top block moving upwards, but we could just as well say the left block is moving downwards. It's entirely equivalent. So we have fault normal of slip vector and then the cross product of those 2. But there are 2 ambiguities. As I just said, you can view the top block as moving upwards or the bottom block as moving downwards, which is equivalent to flipping the fault normal and then switching the slip direction. So that's an obvious one. What What's not so obvious is that if you don't actually see the fault exposed on the ground, if you don't see it sticking out of the earth, the identities of the fault normal and the slip vector actually can't be distinguished, which is something of a surprise. So you can identify these two vectors, but you don't know which one is which. So you identify the normal and the slip direction, but you don't know which one is which. So respecting those ambiguities, you can construct three axes, three orthogonal axes. So that basically the normalized difference and sum of the two key vectors here, the normal and the slip, and then the null axis, which is the cross product. And this is an orthogonal axial frame. So the statistics of this is what this object is what is interesting. The p-axis is the one that's most closely related to the dominant stress that's driving the earthquake. So if you have stress which is normal to the fault plane, the fault isn't going to move because it's being jammed shut by the stress. Also, if you have it stress which is in the plane of the fault, it's not going to move either because it's pressing on both blocks evenly. There's no reason for one to move or the other. It's really, if it's at 45 degrees, you get the optimal sliding of the fault. The fault is going to want to move. All right, so the question is, say, if we've got a set of earthquakes, how can we find the mean p-axis, which is going to tell us something about the dominant direction of the stress? So this is the city where I grew up. This is Christchurch. You can see it down below. Almost all of the tall buildings you can see there have now gone. In the distance of the Southern Alps, that's the backbone of the South Island of New Zealand. And this is what happened in February 2011. It was a mere month before the large earthquake in Tokyo, so I think it rather got eclipsed in the international media. But this is what happened. That's dust rising from the city when this 6.2 earthquake happened under the city, and it triggered a sequence of thousands of earthquakes that went on really for 2 years. It was a very shaky place to live. This cathedral has not yet been rebuilt, but the plans finally are that it will be. Its spire had fallen off once before in an earthquake, but they will not be rebuilding it this way. It'll be rebuilt in something rather different. Okay, so this is now an example of applying these methods to earthquake data. So on the left here we have a stereo net where you can see T's, A's, and P's. So each earthquake is a T, A, and P triplet. You're only seeing one side of it. I'm not showing you the reverse side of each axis. Each axis is plus or minus. So the p-axes are in black, and as you remember, that's the dominant stress. So basically you can see on the left that the dominant stress is horizontal. The mean is of these T's, A's, and P's are in the filled circle. So the P is black. The dominant stress is horizontal, and it's at a slight south to east, so southeast, northwest orientation. The null axis is vertical, so that a-axis that's almost exactly in the center. So you can see where the dominant stress is. If you're away from big faults, the stress is often vertical because it's driven by gravity. But we're on the edge of big grinding plates here, and the stress direction can roll around quite strongly in the presence of mountain building and of tectonic rumpling as one plate dives under the other. So we did a simple test here to see whether or not the stress field had changed before and after the earthquake in February, and it hadn't. So we did a little simple test of that as an example of applying these methods. So we can look at the stress tensor more generally by looking at collections of earthquakes at different places in New Zealand and also over time, which is more or less what I just did. The stress tensor has 6 numbers which define it. It has an orientation. It's like a rugby ball. It's got 3 principal axes: the maximum stress, the minimum stress, and an intermediate stress, and then 3 angles which define its orientation. And it's an oaf. Just like earthquakes that it drives, it's also an oaf. When you're looking at earthquake data, there are only 4 of these are identifiable. You can identify the orientation, and you can identify the stress ratio, which is a sort of triaxiality parameter, which measures the triaxiality of the stress tensor, but you can't get the scales of the stress tensor from earthquake data alone. So one of the things we did was to set up a Bayesian formulation of the problem. So you have a prior for the orientation of the stress. Then you assume that the fault planes themselves are oriented at random. Physics then tells you, if I have a plane at this orientation in a particular stress field, then I know which way it's going to move. And then we allow for measurement error. And we get a posterior distribution for that. When there's no measurement error, you can write that down analytically, and then it just gets messy when there's measurement error, which of course there always is. This is four earthquakes in the same stress field, and then this is showing the direction, the posterior density of the main axis, the principal axis of stress, and we get some indication here that it's somewhat close to horizontal for these earthquakes. And then we can summarize a whole lot of it. For each earthquake gives a contribution to the posterior. So on the left here in this is the San Fernando Valley in California, we get an orientation of the 3 principal axes of stress, S min, S mid, and S max, with just 4 earthquakes on the left. But when you go up to 76 earthquakes, you get much greater shrinkage then of those contours. So that it's very clear that the maximum direction of stress is basically north-south oriented, and the minimum and mid stresses are lying in this east-west plane. Okay, and that led us to a map of New Zealand. So this is New Zealand tilted on its side. There's a lot more goes on the North Island. The North Island is at the right here. It looks a bit like a fish. It's got 2 flappy fins, and its mouth, where I live, that's Wellington, is called the head of the fish, Te Ika Amaui. There are a lot more earthquakes in the North Island than there are on the south. And looking at this diagram, there is quite a strong rotation. So what I'm showing you is examples of the exact equivalent contour map that I just showed you in the previous slide. But you can see in various places across the country, we're getting quite a lot of structure. The Pacific plate is diving down under the North Island at the right, and the Australasian plate is diving down under the Pacific plate at the extreme left, over by the South Island. So there's this very complicated area in the center near Cook Strait that separates the 2 islands, and we get there's a lot of faults, a lot of action that happens in the north of the South Island and the south of the North Island. Okay, so the title of this talk was Ambiguous Rotation, so I'm going to talk a bit more about that. So this work led us to cases where we have even higher levels of symmetry than you have in an earthquake, and to, for example, these crystalline structures and crystalline metals and other minerals. So we're wanting to take these methods to situations where we have very high degrees of symmetry and see how they all work. So just to recall what I said earlier, we have rotation matrices, typically how we describe 3D orientations, but we have these additional symmetries, and we want to respect those when we construct statistical distributions and statistical tests. So the important thing here is we have a point symmetry group K, and any rotation matrix, you can say this is an orientation that represents this crystal. Any of I can multiply by any element of this group K, and these are equivalent. So I represent that equivalence by saying U is a rotation matrix, but the brackets say, and any of the versions of it under this symmetry group are equivalent. So this is SO3 without K. So it's a quotient by the group K. Crystals, if they're going to repeat over a large volume, are restricted to a particular set. So regular solids are only allowed to be one of these sets. So that's a whole lot of notation there, but some pictures here. So the C2 symmetry at top left, that means you're allowed to do one rotation of 180 degrees around a fixed axis. C3 allows you 3 rotations you can do. D6, 6 rotations are allowed, but you're also allowed to turn the object over. That's part of its symmetry. Tetrahedron at the left, lower left, octahedron, that's the cube in the center at the bottom, and the icosahedron lower right. So these are the symmetries we're worried about. Without methods of the kind that I'm describing, the typical approach has been to say, well, I know I have these symmetries. What I'm going to do is I'm going to define a distribution on a directional oriented, definite oriented version of this for rotation matrices. And I'll write down a distribution for those. And then I'll simply apply the symmetry to them and add them all up. And that will give me the distribution I want. It works, but it's not nice in the sense that it's very cumbersome. You're having to do lots and lots of recalculation of similar objects. And when we looked for ways to use the ideas that I told you about earlier to simplify this. So up to now, we've seen the embedding approach for a direction on the plane was to say, let's not just talk about an angle, let's talk about a unit vector. For axes, that meant constructing this object, UU transpose minus a half of the identity, and that's a tensor product of the unit vector. So it's cross product squared of U. That's what we've seen so far. So we're going to just carry on constructions like this using the principles that if we have an R-fold axis, we're going to have an R-fold tensor product. So an axis is just the simple axes we've seen, we're just allowed to have symmetry order 2, but we're going to allow for R-fold symmetry. And we're going to sum over all of the possible axes in the object and then subtract off the expected value of those so that we get 0 if the objects are uniformly distributed in space, randomly uniformly distributed. And that gives us a nice embedding that's got all the properties that I've talked about so far. So an example of this is the C4 symmetry. So this is where you're allowed to rotate 4 times around the fixed axis. The embedded object comes in 2 parts. The first part is the green axis. So that's U0. That's a direction. And it's not ambiguous. I said this is the orientation, and I'm allowed to rotate around this, and I can do it 4 times. Then I have 4 unit vectors, one along each of those 4 directions in the plane. I take a 4-fold tensor product of each, and then I subtract off the thing that I need to subtract off in order to make it 0 under the uniformity. So that's what that object means. That 4/5 of sim is just a constant. Okay, so these are tetrapods. They also have another name. I think it's an acmon or something. Anyway, they're 4 3-fold axes. So we get the 3-fold tensor product, but we're adding up 4 of them. So each object has got 4 axes. I mean, if I give you 2 of them, you can work out the other 2. However, we still construct this object in a symmetric way. We use all 4 of them. And this is the full set of embeddings for the regular solids. So the C, the cyclic ones, and the D with their turning over, the tetrahedron, the cube, and the icosahedron. But we rarely ever actually work with these objects. More often, we just simply go directly to the tensor product, the scalar products that these imply. And the first one is, of course, the one you'll recognize. If I've got a matrix U, it's an orthogonal matrix, and a matrix V, when I go U transpose V, and take the trace of it, this is the object that I get. I'm basically taking, I'm dot producting each of the corresponding columns. So that a C1, that means a fully oriented object with no symmetries. We cannot map it onto itself except by the identity. Further down, it gets more complicated. But the principle is going to be the same. We have a scalar product with a normalization, which we haven't made to be 1. We could have done, but didn't. But here's the good news. Everything looks exactly the way it did earlier. We can calculate means by adding things up. So we take a sample average, and then the sample mean finds the object closest to that averaged object. And a dispersion is written down as simply as that. This is how spread or how not spread these objects are. How am I doing for time? 11:40. All right, so I won't go through these tests, but we have these tests. For example, the 2-sample test is exactly as I described it for the earlier case when we had two samples of axes. Going on from that, we get an exponential family of probability distributions. This generalizes still, again, in exactly the same way the von Mises distribution I showed you right at the very start. It's an exponential of a scalar product multiplied here by a scalar. We can get more complicated than this. The normalization constant C of kappa there is insanely complicated, and we don't have it. We don't have expressions for it. Nevertheless, there are ways to simulate from distributions of this sort. Okay, so an application of this work to texture analysis in material science. So this is 2020 in preparation. 2021, I should probably say, or maybe 2022, who knows. So in texture analysis, so for example, when you heat a solid and cool it, particular steel, it will change its structure, and it's been known for many centuries that if you heat steel up and cool it, it gets stronger. And the reason it gets stronger is because it's changing its structure in patches from one structure to another. And so here's an example of a structure change. So imagine we've got in the plane we have a square cell, a unit square, and that's repeated all over the plane. When we heat it, or we do something to it, that square may rotate, but it also may reorganize. So we can have a square reorganizing into a hexagon. And when this happens, the solid has to pick which one of the two axes of the square it's going to have remaining in existence, as in still parallel to the original square. So a hexagon will have one pair of sides parallel to one pair of sides in the original square. So you can see there are two ways for the solid to choose to do that. Yes, and so this preserves only one of the two axes of one of the two symmetry axes of the square are preserved in the hexagon, but we get two new symmetry axes when we go to the hexagon. And so it could have happened this way, or it could have happened the other way. So there are two ways this square can reorganize itself into a hexagon. So here we go with steel being heated. So we've got the symmetry group is changing. In fact, it's changing from one cubic symmetry group to another cubic symmetry group. The big square there with all the dots on it, that's an electron backscattering measurement of the surface of a steel that has been quenched. So in detail, I don't understand. The beam of electrons is fired at the object, and it comes back, and somehow they get 3 Euler angles at each location on the surface. And what they do is they look at close pairs. So close pairs of points where one part of the pair has changed its structure and the other part is still in the original state. And so the interesting thing is to see whether or not there's been a twisting on the surface and how large that twisting is. So that's the game here. So every black dot in the big diagram there is a place where there has been such a measurement of a transformation from one symmetry group to the other. And this is the particular transformation that's happening. It's going from a face-centered cubic to a body-centered cubic. structure. So this is a face-centered cubic structure. So I've put two cubes here with an atom at each corner, and also the faces of the cubes are occupied. So each cube has got 6 faces, and therefore also 6 atoms, again of the identical sort to the ones on the corners. So I've plotted them in grey, but that doesn't matter. This is the original structure. What happens when the solid is heated and cooled is that, first of all, we can identify a new cube here. This is going to be the cubic cell. Its sides aren't equal yet. There's going to have to be a contraction that takes place, but you can see that this is now a body-centered cell. It's got 8 corner points and then 1 atom sitting in the middle, and its volume is smaller than the original cubic unit, and it has to contract in order to reach its final cubic structure, body-centered cubic structure. Okay, so the original data were orientations of the pre-state and the post-state. That's what these data are. On the left are the pre-state, and on the right the post-state. The colors will become clearer in a moment, but this is just lots and lots of observations of Euler matrices without understanding or taking account of the symmetry that exists. So what we want to do is to estimate the twisting that's taken place between the two states. As the solid reorganizes itself, we get this shift from one state to another, but also a twisting takes place. We're interested in knowing in how many different ways that twisting takes place. So what we do is we need to find a matrix A that is performing the twisting. And this matrix A, of course, is suffering from, or is subject to, or has the property that the symmetries, the left and the right symmetries, the pre-state symmetry and the post-state symmetry, mean that it's not identifiable as a simple rotation matrix. It too has symmetries, and it's in a double quotient space. You lose the symmetries on its left and on its right, the original symmetries and the after symmetries. But basically, the goal is to maximize it. It's to find a value of A that maximizes the scalar product between all these pairs. And when we do that, I take on the left here, we've basically got U transpose V, which is effectively a measure of the distance of the orientation, difference in orientation between the pre and the post. But if you take account of the symmetries, all of that mess on the left sweeps up into just basically 6 groups, 6 different orientations. The red one is almost the identity. So you can see that there are clusters of points at the center, at the left, at the bottom, and top, equivalent patches. That's so cluster number 2, the red one, is almost the identity, but the dominant one is cluster 1 that's in black. That's the dominant twisting that's taking place. 74% of cases on the surface of this were twisting in that way. And this is where the locations were. So the black is the dominant twisting, but there are these other twistings. Group 2 is red, and that's quite widely distributed. Okay, I have a few more slides, but I could actually stop there because they are on a slightly different subject and they're more or less in the slide. So I think perhaps I will stop there, and I'm happy to answer any questions that anyone has.